All right, good morning, everybody. So in the last lecture, we were talking about static factory methods. So a factory method is a method that returns a newly created object. They don't have to be static. So you can have a non-static factory method, but we were talking about static factory methods. And so this slide here shows an example of a factory method that returns a new point given its polar representation. So given its radius or the distance to the origin and the angle relative to the positive x-axis. Right. So notice that the inputs to the method are two double values. And we also have a constructor whose inputs are two double values. So if we wanted to make a constructor that makes a point given its polar coordinates, we can't put both of these constructors in the same class because they would have the same signature. The solution is to create a static factory method and replace one of the two constructors with a factory method instead. Right? And that lets you have both methods. That lets you have the constructor and the method in the same class. If you look in the point2 class, there's a whole bunch of methods that do arithmetic with points and vectors. There's a non-static and a static version of each. So let's just go over there. So here's the non-static version of add. Right? So this version of add adds a vector to a point. Right? And so you would write something like p dot add v. Right? And that would add the vector v to the point p, and that changes p. Right? And so that version of the method, lets you write something like up here. Right? So you want to use that version of the method when you want to write something like p equals p plus v. Right? So this saves you from having to do the assignment to p itself. Right? So this version of the method changes p by adding v. Now you might not want to change p, and so you can supply a second add method. Right? And this time you make it a static factory method. So here we've got another version of add. It's static, so you would call it, I guess, like point2 dot add p and v together. Right? So it's static, so you have to use the name of the class. Right? Because it's static, there's no point object being used to call the method, so now I have to pass in the point object, right? And I pass in the object, the vector object that I want to add to p. Right? And this one lets you make a new vector, a new point q that's equal to the sum of p and v, and it doesn't change p. Right? And so that lets you, that's why there's for every non-static method that does some arithmetic, there's a corresponding static method that does some arithmetic as well. Right? One changes the point that was used to call the method. The other one does not change the point and the vector added together. Right? Instead, it returns a new point. So if you're looking in the point2 class, that's why there are that's why there's a static companion method to all of those methods there. Right? Finally, if you look in the Java standard library, many classes have static factory methods in them. So the integer class, all of the wrapper classes have a method called value of. Right? Value of takes it for integer. Value of takes in an int and returns the integer object corresponding to that int. Right? So when you do something like integer I equals 1, the compiler is silently calling this version of the method for you. Right? So it's silently calling that static factory method to produce a new integer, sorry. Right? Arrays has a bunch of static methods in it. One of them is copy of, so that will copy an array and give you back a new array that's equal to the copy. And string also has a bunch of static factory methods as well. Right? So string format, that's the method that looks a lot like C's printf method. I guess it would be sprintf, so print to a string. It's a formatted print to a string. So Java's version of that method is called format, and it's a static method as well. All right, so that wraps up the lecture on static features in a class. We're almost, but not quite done implementing basic classes. So there's a couple of other things I have to tell you about. So one of them is, what does it mean for two objects to be equal? And how do you implement a method that determines if two objects are equal? So the method that you use to determine if two objects are equal is called equals. All right, so you write a new class. I've told you already, every class that you create in Java, whether you say it or not, is actually a subclass of big O object. So in Java, we say it extends object. Right? Now, object defines this method called equals. So that means every object that you have, you can use equals with that object. And so for our point2 class, we can write, does P equal P? Right? So does P equal itself? Right? Hopefully that's true. Okay. So if I write P2 equals P, right? Now remember what that means. Right? That means P2 is just another name for P. Right? So P2 and P are both refer to the same point. So P2 equals P, well, hopefully that's true as well, right? Because that's exactly the same thing as saying P equals P. But if you make a new point object that has the same coordinates as the original point, and you ask, is that new object equal to P, you will now get the answer false. Right? And so the version of equals that you get from object normally doesn't do what you want it to do. Right? And so what the version of equals that you get from object tests for is, do both references refer to the same object? Right? And so in the code from the previous slide, right, P is here. Right? P2 is the same point, so it's also that one. But P3 is that point down here. Right? So P has address is the point that lives at address 600, and P3 is the point that lives at address 700. Right? They have the exact same state, so their coordinates are 1 and 2, right? But they are different objects. So when you ask, does P3 equal P, the answer is no, because equals is asking, are these things the same object? Right? So object equals checks if two references refer to the same object. You might see this referred to as equality of identity. Right? So are the two objects the same object? Right? And that means x equals y is true if and only if x and y are references to the same object. Right? It's basically asking, it's basically the same thing as saying, is P equal to P? Right? Okay, now when you're implementing a class like point2 that represents a value, right, you probably want to ask, you probably want equality to be logical equality, right? Do the two objects have the same state? Or do the two objects have equivalent state, not necessarily the exact same state? Right? So an object is equal to another object if their states are equal. So for points, you probably want to ask, are 2 points equal? If you ask, are 2 points equal, you probably mean, do they have the same coordinates? Right? So if you want to ask that sort of question, you simply replace your implementation of equals. Now, when you go to do this, it turns out to be surprisingly complicated. And so in the early days of Java, this quote comes back. This quote is from, I don't know when she wrote this, but it's relevant to the 1990s when Java was starting to become, I guess when Java was created and starting to become more commonly used. So Angelica Langer, she's a Java consultant, well, she's a software consultant. She's got a blog, she's got an article which you can which you can find by clicking that link there. Right, and she says that one would expect that overriding equals, since it's pretty common, should be easy, right? I mean, I just want to know, do 2 points have the same coordinates? Right? And so she goes on to say, the reality is far from that. There is an amazing amount of disagreement in the Java community regarding the correct implementation of equals. It used to be the case that if you picked up a textbook for Java, and you picked up a second textbook for Java and looked at how to implement equals, they would both tell you something completely different. Fortunately today, everybody has decided that there's basically two basic ways to implement equals, and then there's a third general approach if you need a very complicated version of equals. Right? We're only going to talk about the two basic approaches. Okay, so what we do today doesn't always do exactly what you want it to, but it satisfies the equals contract. So the equals contract is just the specification that's in the object version of equals, which I guess is worth looking at. So if we go too many windows open. So if we look at the documentation for the class object. Okay, there's equals. So here's the class big O object. There's the equals method. If you click on that, you end up with this fairly long description of exactly what equals ought to do. Right? The description is actually mathematical. And so I guess if you're familiar with what all of this means, that's great. But for the average programmer who hasn't done this type of math, this is sort of, this needs some explanation, which I will try to do in the rest of this lecture. So that is the specification for equals. Anytime you replace equals, it must satisfy this specification. Right. Okay, so notes. This is an old slide. The Jupyter Notebooks, I think, actually does it a different way. So it's going to do it the second way that I show you. For today, we'll do it the straightforward. We'll do it the way I'm about to show you. So this is what we require for equals. An object should always be equal to itself, which kind of makes sense, right? It would be very unusual if you implemented a class where an object was not equal to itself. Right? If you write x equals null, that should always return false, and it should never throw an exception. Right? So an object is never equal to null. For today, we're going to say that two objects can be equal if they have exactly the same type. So 2 points can be equal, but a point can't be equal to a vector, right, for example. And then finally, we're going to say that two objects are equal if they have the same state, right, if their state is equal. Okay, so requirement number 1, x equals x should always be true, right? And similarly, x equals y is true if x and y are the same object or refer to the same object. Right? So that is what the Java's double equals operator does. Right? So if you write x equals y, it's testing for two references. It's testing, are they the same object? Right? For primitive values, it's testing, do they have the same value? Okay, so I need to return true if the two objects if the two references are the same object. Now remember how you're going to call equals, right? So you're going to write something like, let me just pop over to Eclipse. I need an empty class somewhere. This is the matrix class. I'm just going to, well, I just need to insert a main method somewhere. I guess we'll make a matrix object. M equals new matrix. 1, 2. Right, and we'll make a second one because why not? Let me call them A and B. Right, so this just makes two, well, we don't know what it does actually, but it makes two matrices with the same size. Let's assume that they are all zeros. Right, so you're going to do something like A dot equals B. Right? So that's how we're going to use equals. Now when you call equals, right, A is the object that you use to call equals, right, and B is the argument. Right? So inside the equals method, this is simply A, right, the object that was used to call the method. Right? So, oops, sorry, back again. Up here. Okay, so if A and B are the same object, right, inside the method, A is this, right, and inside the method, B is obj. So if I want to test are they the same object, I want to write if this equals obj, right? So that tests whether or not the two objects are the same object. And if they are, we can simply return true. I guess the thing that I didn't point out is that equals always looks like that, right? So it's always public Boolean equals big O object obj. Right? The name obj here is not important. You can just use O if you want to, or something else. Right? But it's always public. It always returns a Boolean value. It's always named little e equals, and its parameter is always big O object. Right? A very common mistake is that people change the parameter. Right? So if you're in the .2 class, they'll say public Boolean equals .2, right? And that's completely wrong because you're no longer replacing the version of equals that you got from big O object, right? You're now creating a new version of equals. So you're creating an overloaded version of equals. You're not overriding the existing version of equals, right? It's very important that you override the existing version of equals. So the signature must look exactly like that. Right. Okay, so there's requirement number 1 taken care of. So that was easy, right? It's just one if statement. Requirement number 2. If you write x dot equals null, you must return, equals must return false, right? And it must not throw an exception. Right? So one of the requirements of equals is that it never throws an exception. One of the reasons why this is a requirement is because a lot of the standard library methods use equals internally. Right? If you're searching a list for something, the list is calling equals on every element in the list. Right? So if you're binary searching an array, the binary search method is using equals to determine whether or not you found the element that you're looking for. Right? And so the standard library is written assuming that equals never throws an exception. So if you are replacing equals, you must never throw an exception. Right? All right, so if that is one of our requirements, then it looks like we should probably test whether or not obj is null. Right? So if obj is null, return false. Right? That's how you test something for null in Java. Right? So you can write obj equals equals null if you want to test if it is equal to null. And you can write obj not equals null if you want to test if it's not equal to null. So we return false if we get null as our argument. Right? And then notice this prevents any exception from being thrown. Right? That'll never throw an exception because it's just, we're just using the equality operator. Right? Again, that'll never throw an exception because we're using the equality operator. If obj is null, the method stops, and so no exception is ever thrown. Right? If you don't put this test in, and if you don't put it here, you can put it before, but it doesn't make sense to put it before. If you don't put it here, and you put it after the next step, you'll end up throwing a null pointer exception. Right? And so that's why it shows up second in the implementation. Okay, part 3. Instances of the exact same type can be equal. And objects that have different types cannot be equal. So we're going to relax this restriction later on, but for now, this is the restriction that we're going to live with. Yes?
Like, primitive types like int be equal to the wrapper classes integer?
Yeah, but that's handled specially. Yeah. All right, so now this requirement is basically saying you have to be able to determine the type of the incoming object. Right? So remember, the incoming object, as far as we know, it's just big O. Right? It's just a big O object. Right? So now we have to get the actual type of the incoming object. Right? So if someone writes here, A equals B, right? B is actually a matrix, right? It's actually a big M matrix. Right? So we need some way to determine the actual type of the object that's coming in. Right? As far as the method is concerned, it's a big O object, right? But it actually has some other, it probably has some other type, right? And so we need to determine that other type, right? And so the way that you find out the type of something in Java is you use another object method, and that one happens to be called getClass. Right? So getClass returns a funny-looking return type, right? So you can't, we can't understand that notation at this particular moment. So just ignore all this question mark extends object nonsense, right? In like week 11 of the course, you'll finally be able to understand what that means. Right? So for now, it returns a class object, a big C class object. Right? And so this method here, it says it returns the runtime class of an object. So the way that the language works is that every time you use a class, so we use the, I don't know, the point2 class in our program, the point2 class gets loaded into memory, and then a new class gets, a new object gets created. That new object is one of these big C class objects, right? And it stores information about our point2 class, right? So every time you use a class, you get a corresponding big C class object that stores information about the class you're using, right? One of the things it stores is the type that you're using, right? And so you can get the type of an object by calling getClass. And so that looks easy. So we can just use getClass. that'll determine the class of obj. Right? So I'm going to ask obj, hey, what is your actual type? Right? Now, it has to be equal to point 2. Right? So, because we're inside the point 2 class, and we're saying only point 2 objects can be equal to themselves. So the way you get the class of point 2 is you write this dot get class. Right? Remember, this is the object that was used to call the method. Right? So you can call get class on it to get its type. Right? So if its type is not equal to the other type, then you know that the two objects have different types, and you can return false. Right? That might make you wonder. Right? So why are we allowed to use not equals here? Right? Because this is actually an object, and that's actually an object. And if you're comparing objects, I've told you you're supposed to use equals to compare the two objects. Right? But here we're using not equals. Right? So the reason you're allowed to use not equals here is because of the way get class works. Right? So if you actually look at the documentation for get class promises that for every class in your program, there is exactly one big C class object that corresponds to that class. Right? So in other words, if you call get class on any point, right, on any point object, you always get back the exact same big C class object. Right? If you call get class on any string object, you get back the exact same class object. Right? There's only one class object for every class in your program. So that means you don't care about the state of the class object. There's only one of them. Right? There's only one for point 2, there's only one for string, there's only one for big O object. Right? And so you can safely use equals, equals, or not equals in this case. Right? This is one of the confusing things about the Java language. Right? The fact that equals equals exists and dot equals exists is very confusing. Right? And you really need to understand what is the difference between the two to determine whether or not you can write that sort of thing when you're dealing with objects. Anybody have any questions about what I just said? That's a pretty subtle point that's going on in the language. All right, so we'll continue. Next step. Okay, so notice that equals takes in a big O object, which is annoying, right? At least from the perspective of implementing equals. So the fact that it takes in a big O object complicates our life because we want to test, right, are the coordinates of this point the same as the coordinates of that point, right? We know that's a point if we reach this line here, right? Because if this if statement, if that condition is, well, if we return false from here, then we know that that's not a point 2 object, right? If we don't return false from here, then we know here that's a point 2 object, right? And so I would like to get the x and y coordinates of that thing, but the compiler won't let you. Because as far as the compiler is concerned, obj is a big O object, right? It's not a point 2 object, right? We know for sure that it actually is a point 2 object, right? But we told the compiler back here it's a big O object, right? And so here, we have to now convince the compiler that this thing is in fact a point 2 object, right? So how do you do that? You use a cast, right? Just like you would do in C. So here we're casting obj to a point 2 reference, right? You're allowed to do this here because you got past this if statement here. Right? If you try to do this before checking are the classes the same, and when you do the cast at runtime, the cast will fail at runtime. Right? So when your program runs, you do an incorrect cast, you'll get a class cast exception. Right? In other words, the Java virtual machine is trying to tell you, hey, that thing's not really a point 2 object. Right? Here we know it's safe because we got past this if statement here. Right? And so this if statement must be here. Right? The second if statement has to be here, right? Because we're testing is obj null. Right? If it is null and we don't have the test, then obj get class fails. Right? You would end up writing null.get class, which is guaranteed to throw a null pointer exception. Right? So that test must be there. This test must be here, right? This test has to be here, otherwise this test fails with an exception. This test must be here, otherwise this test can fail. This cast can fail with an exception. So the order in which you do things is critical. And to simplify your life, you always do the exact same thing in that exact same order, right? So when you implement equals, you don't think about it at all for the first 4 steps, right? You write that, then you write that, then you write that, and then you write that, right? And then only in the next step do you actually have to do any thinking. Right. All right, any questions so far? Okay, the final step. Instances with the same state are equal. And so you now run into another annoying Java thing. So there is a standard recipe for testing whether or not your fields are equal, right? So what I want to do at this point now is I want to compare the x and y coordinates of this point to the x and y coordinates of the other point, right? So you might want to write something like if this dot x equals other dot x, right? And this dot y equals other dot y, return true, right? Because that's how you would test if 2 double values are equal. Unfortunately, things are slightly more complicated than that, right? Okay, so there is a recipe for doing this, right? Basically, you want to go one field at a time and test whether or not the fields for the 2 objects are equal. Right? So if your fields are primitive, which ours are, right? If they're not float or double, so in other words, if they're integers or if they're Boolean values, then there's no thinking involved, just use equals, right? So just compare them the way you would normally compare them. Right. If you have 2 floating point values, which is the situation we're in, right, then what you're supposed to do is to, if you have a float type field, you call float to int bits, and if you have a double field, you call double to long bits, right? And what these 2 methods do is that they safely convert a float to an int value, and this one safely converts a double to a long value, right? Now when I say convert, I don't mean you get the same numeric value when you do the conversion, right? And so what these methods do is it takes your floating point number, right? So if you have a float, it's 32 bits, right? And it simply reinterprets all the bits as though it were an int instead, right? That does not give you back the same floating point, right? So that means the int value you get back is not the same as the floating point value that you used, right? The values are different because it's reinterpreting the bits, right? Double to long bits does the exact same thing for double. So a double is 64 bits. So it interprets those 64 bits as though it were a long value, right? Again, the value that you get back is not necessarily the same, right? So all it's doing is reinterpreting the floating point number, the bits of the floating point number, as though they were the bits of the corresponding integer number. Right. I'll explain why you have to do that in just a second. If you have arrays, so if you have, if your fields are of array type, then you can use the method arrays.equals to compare them. This is only true if you have a one-dimensional array. If you have a multi-dimensional array, it becomes harder. Right? And finally, if you've got reference type fields, which we haven't done yet, right? But if you have objects as your fields, then you're just going to compare the objects using equals. Okay, so why on earth do I have to do this conversion from floating point to integer nonsense? Right. So why do I have to do this? It's because of the way that floating point numbers work. Right. There's a couple of main reasons. So one is that if you compare not a number to not a number, the IEEE standard says you always get false. Right? The standard says nan is never equal to anything, even itself. So if you were to use equals in your method, and you happen to have 2 not a number values, your equals method will automatically return false. Right? Which is probably not what you want to do, but it might be. It's probably not. Right? Admittedly, this is almost never going to happen, right? Or it's very rare that this will happen. Okay, so if you call double to long bits and you pass in not a number, right, that converts whatever not a number is as 64 bits and converts it to the corresponding long, right? And so when you do the conversion and compare it to itself, you're always going to get back the same long value. So nan equals nan compares as true if you do it this way, which is probably what you want. right? So imagine if you had 2 points and their coordinates were both not a number, and you wanted to compare them, you probably wanted it to return true, right? If you just use equals equals to compare the coordinates, you're going to get back false, right? The other reason you want to do this is because the IEEE standard says -0 is equal to 0, right? Whereas if you look at the bit pattern for -0, that's different than the bit pattern for 0, right? So when you compare these two values, you get back false. Now, admittedly, this might not be what you want, right? You might want 0 and -0 to compare as equals, right? But every standard library class that implements equals does it this way, right? And so the rule is you should try to be consistent with the standard library, right? In order to be consistent with the standard library, to compare floating point values, you have to do something like this instead. So what does it look like? It looks unnecessarily complicated, right? But this is the way you do it, right? So here I'm going to test whether or not the x-coordinate of this point is different from the x-coordinate of the other point, right? Now remember, other is just obj cast to a point, right? If they're different, I know that the 2 points have a different x-coordinate, so I can immediately return false. Right? I'm then going to do the exact same thing with the y-coordinate, right? So is the y-coordinate of this point different than the y-coordinate of the other point? The answer is yes. I'm going to return false, right? I've now compared all the fields, right? All the fields are apparently equal, so now I can return true finally. Right? And so there is your standard version of implementing equals. Okay, so that version of equals compares the state of 2 points to determine equality, right? If you have 2 points with the same coordinates, they're now equal, right? So here we make a point whose coordinates are -1 and 1.5. There I use the copy constructor to make a copy of the point, right? So P and Q, they now have the same coordinates. So P equals Q will now print out true, right? If you were to run this program and you didn't override equals, P equals Q would be false because they're different objects. Right. All right, so the equals contract. So if you actually read the documentation for equals, it says that equals must be the following things. Right? Must be reflexive, symmetric, transitive, and consistent. Right? Furthermore, it must not throw an exception when past null. Right? And so the first three things here all have a very particular mathematical meaning. Right? In simple terms, this is what these things mean. Right? So reflexive simply means that an object is equal to itself. Right? So x equals x is always true. Right? That was our requirement number one, which we've already satisfied. Right? Symmetry means two objects must agree on whether they are equal. Right? So x equals y is true, right? If and only if y equals x is true. In other words, it doesn't matter if you reverse the order of the two arguments. You should always get back the same answer. Right? This is only true if one of them is not null. Right? If one of them is not null, then that's handled by the fifth case. Right? Now, if you go back and look at our implementation back here, right, and you ask yourself, is this thing symmetric? Right? And you should be able to convince yourself that, in fact, the answer is true. It is symmetric. Right? So this version of equals only compares points. Right? So if I have a point dot equals some other point, it might return true. Right? But if I have some point equals a string, that's going to return false. Right? Or a string dot equals to a point, that should also, hopefully that also returns false, but you don't know that unless you look at the string implementation of equals. Right? So assuming you have 2 points, right, does this thing return true? Does P equals X, P equals Q give you the same answer as Q equals P? Right? And so you just look at your two comparisons here. Right? And so these two comparisons are also symmetric. Right? If this dot x is not equal to other dot x, then it's also the case that other dot x is not equal to this dot x. Right? And similarly for this y and other y. Right? So that version of equals is symmetric. Right? It's not clear to you, it's probably not clear to you right now, but it's that line here that actually guarantees symmetry. Right? in a few weeks, hopefully I remember to come back and you'll understand why it's that line that guarantees symmetry here. Okay, transitivity. So transitivity means if the first object is equal to the second and the second object is equal to the third, then it must be the case that the first and second and third objects are equal. Right? So if x equals y is true and y equals z is true, then it must be the case that x and z are also equal. Right? Again, if you go through the implementation of the method, you can convince yourself that the method is in fact transitive. Right? The consistency requirement basically means equals must not be random. Right? So if you compare two objects over and over and over again, and you never change the two objects, then equals should always return the same answer. Right? If the state of the objects change, then obviously the answer might change. Right? If the state of the two objects never change, then equals always gives you back the same answer. Right? And finally, the non-nullity requirement means x equals null always, is always false, and it never throws an exception. Right? Okay, what about the counter version of equals? So the counter version of equals is easier than the point version of equals, right? Because you don't have to deal with this nonsense with the floating point field. Right? So what does it look like in counter? Step 1, 2, 3, and 4 are exactly the same as for point 2. Right? The first 3 steps are even exactly the same code. Right? You check, are the two objects the same object? And if they are, return true. Right? You test, is the argument null? And if it is, you return false. Right? You test, are the two objects the same type? Or do they have the same type? If they don't, you return false. Right? Step 4 is the cast. Right? So tell the compiler that, hey, OBJ really is, in this case, a big C counter object. Right? And now, in the final step, is where you compare the fields of the object. Right? Counter has one field, and it's an int. So you can simply write, return this value equals equals other value. Right? If they're the same, it returns true. And if it's false, it returns false. Right? Okay. Now, when you go to do this in Eclipse, so this is one of the funny things with this course, right? So on a test, you kind of stuck having to memorize the first 4 steps, right? In practice, you never memorize the first 4 steps, right? So in practice, you ask your IDE to do this for you. So I need to insert a field here. So let me just insert a field. So our matrix class is not going to be very good, right? In fact, it's going to be a 1-by-1 matrix. So I'm going to have one element in my matrix, right? Okay, so that's my one field. Obviously, this is not a complete matrix implementation, right? For rows, I'm going to return 1 because our matrix has exactly 1 row. Right? So when you go to implement equals for this class, you could start typing in equals, right? And you should probably do this a few times so that you actually remember what this looks like, right? But if you find yourself actually programming a class and you decide it needs equals, ask Eclipse to generate it for you, right? So under source, generate, hash code and equals, right? You might ask, why is it generating hash code? Well, I'll give you the answer to that in the next lecture, right? Okay, it'll then ask you, okay, so if you're implementing equals, which fields do you want to compare for equality? Well, my class only has 1 field, so I'm just going to pick that one. Click generate, and voila, there's equals. Right? And it does exactly what I just showed you. Right? Tests, is this object equal to the incoming object? It tests, is the incoming object null? It tests, are the classes of the two objects the same? It performs the cast. Hey, look, it even does double the long bits for you. That's awesome. Right? So it does that conversion for you, and then finally it returns true, assuming the fields are in fact equal. Right? So Eclipse will generate this method for you. It usually generates the correct version of the method for you. Right? The first 4 steps are always the same, so you never have to worry. Oops, sorry. The first 4 steps are always the same. Right? So whether you're doing this by hand or whether you're asking your editor to do this for you, it'll always look the same way. Well, sorry, step 3 can change, but more about that later. Right? The only part that might change is this part here, when you start to compare the fields. So it's possible to have an unusual class where you decide you don't want to compare all the fields, right? Or you decide that two of the fields, when you compare them, you're not necessarily looking for equality, but you're looking for something else, right? And so you can run into unusual versions of equals where comparing the fields is not exactly, is not as straightforward as saying, is this field equal to this field, is this field equal to this field, and so on and so on and so on, right? And so that one, you can run into some complications here, right? So if you start out with the Eclipse generated version of the method, you might have to edit step number 5? Yeah, the 5th step, right? Where you determine whether or not the fields are equal, right? But otherwise, everything else always stays the same, right? So remember those 4 steps, right? It's pretty much guaranteed that you're going to get asked about them on a test, right? Okay, so that is the first, oh wait, the hash code, right? So notice that Eclipse, when I asked it to generate equals, it didn't let me generate equals without also generating hash code, right? And so the hash code method is a funny method. So it's a method that the typical programmer will never use, right? So you will never call hash code directly yourself, right? And so the question is why on earth is this here, right? So reason number 1, it's here because it's also in big O object. The reason it's in big O object is because the Java standard library has a bunch of collections in it that are that use hashing, right? So there's a hash set, there's a hash map, and there's a bunch of other hash collections as well. The way that all of those collections work is that it calls this method called hash code, right? So if you know what a hash table is, this is how Java implements part of the hash table algorithm, right? It requires every object to be able to convert itself to an integer value. That's essentially what this does, right? And so it turns out that if you change how equals works, then you must also change how hash code works. And that's why Eclipse forces you to generate both of these if you ask it to generate either one of them, right? And so I will, in the next lecture, explain exactly what hash code is used for and why you have to generate both if you decide to replace equals. Okay, that's all I want to talk about today, so we'll end class a little bit early. So next week, I guess, yeah, next Monday, we'll talk about how hash code works and why you have to implement it if you're implementing equals.